Okay, so each hydrogen had one electron to contribute because they're in group 1. Carbon was in group 14, so it has one electron on each side, so 4 total. And you get single bonds on between each carbon and hydrogen. So this is the proper Lewis structure for methane. I want you to do the same thing for water, rubidium and bromine, and lithium and chlorine. Now remember that it matters if the compound is covalent or ionic. So the first thing to really ask yourself is, which one is it? The best way to determine that is using electronegativity. So for example, carbon has an electronegativity value, let me pick a different color you can see a little better, electronegativity of 2.4. And the other element we were using is hydrogen. It has a value of 2.1. So I'm going to subtract those two. Okay, so we get a difference of 0.3 in that bond. That means that this bond is polar because it has a separation in charge. If we had an electronegativity difference of 0, then it would be nonpolar. So 0 means nonpolar. Anything bigger than 0, but smaller than, say, roughly 2, so any 0 to 2, is called polar covalent. So that tells us what kind of bond it is. Nonpolar bonds are also covalent. Okay. And then anything bigger than 2 is considered ionic. Okay, so there's a nice figure in my Chem 111 notes, if you had me, that details this in a much more visual format. But those are our cutoffs. Okay, so for this methane here, this individual, oh, by the way, you can also draw it like this. This is equally valid. A little neater, maybe. So with our methane here, this CH bond, each one of them actually, is identical, but they all have a difference of 0.3. So each one of those bonds is polar, covalent. Okay. Sometimes it's convenient to calculate whether something is ionic or covalent to begin with, so you know whether you should draw the electrons as shared, like this, or whether you should draw them as an ionic bond, like this. Okay, so it's really a handy way of figuring out how to draw your structures. So, referring back to the Lewis structures that you drew, I want you to determine whether each bond in these 4 is covalent, which means nonpolar here, so nonpolar covalent, polar covalent, or ionic. Okay. And again, if you figure out something is ionic, don't forget you have to draw the structure differently. All right, so nitrate is one of the polyatomic ions on the back of your periodic table. And we said that the first element is usually the central element, so I'm going to write that down first. Nitrogen is in group 15, so therefore it has 5 valence electrons. And I can see that this nitrogen needs 3 more to have sort of the stable octet that it's looking for. So what I'm going to do is put those 3 oxygen in those kind of open spaces, right? So 1 oxygen here, 1 oxygen here, and 1 here. And the oxygens are all in group 16, which means that they have 6 valence electrons. I don't know why this keeps changing size. Sorry about that. Okay, so right now the way I've drawn it, the nitrogen has the octet that it wants. It has 8 electrons around it, 2 on top, 2 on each side, so that's 8. But each of the oxygens is miserable because they only have 1 bond, and we said that oxygens need 2 bonds. So that means, it's only got 7 electrons, not 8 that it wants. It turns out nitrogen is really pretty good at handling multiple bonds. So we can connect one of these electrons on the top with adjacent oxygens. You could do the same thing over here too. And so if we draw that a little neater, we have nitrogen. One possibility is to have two double bonds and a single bond. The ones that are double bonded have two valence electrons, like this. And initially it looks like the single bonded oxygen has still only 7 valence electrons. However, we forgot to include the negative sign on your polyatomic anion. So that means that that negative electron, that extra electron, must belong to the single bonded oxygen. I want to show that this whole thing has a negative charge by putting it in brackets with a minus sign. Now, this isn't the only possible Lewis structure for nitrate, actually. There's many, many, many of them. So, for example, you could come up with an equally valid structure that looks like this. I'm not going to draw all the valence electrons in there, but you can figure out where they go. These are both equally valid. There's no reason to say that this bottom oxygen doesn't get the double bond. So that means both of these structures exist. In fact, the electrons move around over time. So that double bond can be on the left and then it can switch to the bottom. So we call that resonance. Resonance structures are very, very stable. So anytime you can draw more than one valid Lewis structure, that's actually a good thing. Okay, so those are reminders of what we already know. Most of the polyatomic ions in the back of your periodic table have resonance structures, things like sulfate and phosphate. And that's why they're so stable. That's why they exist the way they do. Another example is if we take that polyatomic anion, the the NO3 here, so it's still the nitrate, and we connect it to a sodium, we make a compound. The Na doesn't connect to any one particular oxygen. It's going to kind of loosely associate with all of them. So that's why we don't draw Lewis structures where the Na shares electrons with any other particular part of the nitrate, because it kind of cruises all over the place, really. Okay, so this is probably the best way to represent the Lewis structure for this compound. It's two completely separate molecules, two completely separate particles, rather, not molecules. All right. Now, when things dissolve in water, this ionic bond, this connection between the sodium ion and the nitrate ion is what dissolves. That's what breaks up. The polyatomic ion stays together entirely, so that's important for us to remember as we go forward. Okay. So, covalent bonds never break. I want you to answer this question. Why do you think covalent bonds don't break, but the ionic bonds do? So, like for this example, identify, number one, what is the ionic bond in this compound? So what breaks? And what is covalent in this compound? So what doesn't break? And then I want you to also tell me why don't covalent compounds break? Okay. We're not going to cover the rest of this lecture, the purple lecture, right now. We'll come back to it in about a week or two. So don't trash the notes. Keep the rest of the paper. All right, so for the rest of this week's task, we've got to delve into what gases are. And this is new material, so it's not from 111 at all. So gases were initially explored by a lot of different scientists in the early 1800s. In fact, PBS has a really fascinating series all about how gases were initially quantified, because if you can imagine, these things are invisible and completely not understood. They were considered kind of magic, actually, in this time period. So all these Victorian scientists started doing things like generating random gases and then inhaling them to see what happens. Well, the guy who did that actually died clinically twice in this process, so he had to hire a nurse to, resuscitate him. But he's actually responsible, interestingly, for discovering laughing gas. So all these, rich guys in Victorian clothes sitting around huffing laughing gas. So it's a pretty funny image. Also, he discovered carbonation, like in your soda. he figured out if you take CO2 and shake it in water, the water gets fizzy and delightful. That's a quote. So they did kind of like really random things because gases were not understood very well. We know more about it now than your average really well-educated scientist did in the 1800s. So you know what a gas is because it's a familiar concept. We talked in 111 about various characteristics, like it has an undefined shape, meaning whatever the container shape is the shape that the gas will have. If I put gas into a heart-shaped container, then it's shaped like a heart, or a square, whatever. It also has an undefined volume, so if I take the same amount of gas and I move it into a larger container, it'll occupy the whole container. We also said it's compressible, which means we can squish it. Remember, it's the only state of matter that can be squished. Liquid and solids cannot. Okay. So those are some of the characteristics. Oh, also, we decided that gases are highest in energy of all the states of matter. So that's an important thing to remember. When we're talking about gases, we have to measure pressure in order to talk about them. And it turns out there's a special quantity called standard pressure. And so this phrase, which is sometimes abbreviated as SP, this phrase literally means exactly 1 atmosphere of pressure. Oh, we already got the answer to this. Energy is related because gases have the highest energy of all the states of matter. Okay, so 1 atmosphere of pressure was not the first unit of pressure invented, actually. The first one is something called millimeters of mercury, which is also known as torr. Now, to get this, what they would do is they have a pool of mercury. So this is, mercury, the toxic stuff that used to be in thermometers. And what you do is you take a glass tube that has nothing in it, so it's a vacuum, and you put it into the pool of mercury, and the air pushing down on this pool forces the liquid up into the glass tube. And the height that it goes up is proportional to how much pushing the air is doing. So you can literally measure this height and determine how much pressure the air has at that moment. So we call that millimeters of mercury. And it turns out, also torr, by the way. You should know that those two are synonyms. It turns out that later on we developed an atmosphere because it was a little bit of an easier number to imagine, and we said that the standard pressure at sea level happens to be about 760 torr most of the time, so 760 millimeters of mercury. And so that is our definition for standard pressure. It's 1 atmosphere or 760 torr. They actually mean exactly the same thing. Okay, so that's kind of the way back ago definition of pressure was torr, and now we also use atmospheres. Now, a lot of the time you'll actually see something even stranger. It's called kilopascals, and the reason that kPa is used is because it's related to the most basic units of measurement in the SI system, things like meters and kilograms and seconds. So 1 atmosphere equals 101.3 kPa. If I wanted to know how many pascals that is, I have to know what the K means, right? And so we'll remember from 111 that K means kilo. Okay, so K means kilo. So I want you to convert from 101.325 kPa into just plain PA. Okay, and finally, in America, we also use PSI. Your tires, for example, probably need to be filled to about 36 PSI. Maybe 32. It depends on your car. So we can use this relationship as a conversion factor, right? You can say 1 ATM on top and 14.696 PSI on the bottom. And so tell me, what is my tire pressure supposed to be in atmospheres? Okay, so fill that in on your worksheet.